Yeah, hello everybody. This is Maxim Ballmer, and I will acknowledge my co-authors, which you see on the slide. The title of the talk is Crystallization Sequence of the Basal Magma Ocean in the Light of Geochemical and Geophysical Constraints. Next slide. So this is just a quick picture. So if you're not interested after this slide, you can stop watching the presentation, however long it will be. I'm just in the process of recording it. So the take-home messages are, well, there's a problem which I will show in the beginning of the talk. Fractional crystallization of the Basal Magma Ocean should result in a long-lived basal layer, but such a layer does not exist on Earth, at least as we can tell from geophysical observations. Then I will discuss one potential solution, that there is a disequilibrium, a chemical disequilibrium between the mantle and the Basal Magma Ocean, and then there is some reactive freezing instead of, so reactive crystallization instead of crystallization due to cooling and isolation of the Basal Magma Ocean. And then I will move on to an alternative solution for that, which works even better. And I will also acknowledge that my students Matteo and Anna are due to give talks in this conference, and I will advertise that again on one of the later slides. So let's start with the Basal Magma Ocean hypothesis. So the Basal Magma Ocean basically sets the initial condition of long-term mantle evolution, mantle convection, the fractional crystallization of the magma ocean, of the Basal Magma Ocean, and maybe the remnants of the Basal Magma Ocean are still observed today. A Basal Magma Ocean has been recently also suggested to have been formed on Venus, and maybe on Venus even there on the present day. At least that's what a recent paper says by Joe O'Rourke. And also Mars. There's a recent paper, for example, by Henri Samuel and co-authors. The presence of a Basal Magma Ocean on a planet has implications for its seismic properties and tidal lava numbers. There are several different ways of making a Basal Magma Ocean. It depends exactly where the density crossover between solids and liquids is, whether you have fractional crystallization in the lower mantle or batch crystallization in the lower mantle, so at which porosity you equilibrate the two, and also at which depth the adiabat and the solidus intersect, or in other words, at which depth the liquid is, for fractional crystallization, at which depth or pressure the liquidus becomes steeper than the adiabat or isentrope. Well, then you might be familiar with this hypothesis that the first crystals float at the density crossover. Depending on scenario, you have a variably thick and iron-enriched Basal Magma Ocean. For batch crystallization, basically, where you first quench the magma ocean in the lower mantle basically to a mush, and then the crystal mush segregates by compaction, downward compaction of dense liquids, you would obtain a much thicker Basal Magma Ocean, more voluminous and more massive. So a BMO should be common in terrestrial planets. Oh, sorry, I think I skipped the last scenario. Kind of skipped itself. Well, if you just have, for example, the density crossover is greater than 135 GPa, or you're in a planet that is smaller than the Earth, core mantle boundary pressure is lower than for the Earth, and you can still get a Basal Magma Ocean by an overturn of intrinsically dense top magma ocean cumulates. And then you remap that at the bottom. But the size and the chemistry of these of the Basal Magma Ocean depends on the formation scenario, and we really don't know. There are many arguments to say that there was a Basal Magma Ocean, but we don't really see. We don't really see if the Basal Magma Ocean crystallization is consistent with observations, and I actually will convince you that at least in the simplest scenario of basal magma ocean crystallization in isolation, so just fractional crystallization of the basal magma ocean, mostly isolated from the mantle, this is inconsistent with present-day geophysical observations. Why is that? So if you have the mantle and then crystallize the basal magma ocean by fractional crystallization, the basal magma ocean crystallizes slowly or cools slowly, so it should really crystallize by fractional crystallization if it's isolated. Well, then you get this, basically Rayleigh distillation effect, and the basal magma ocean becomes more and more enriched in iron, and so do the cumulates. So just play this again. Basal magma ocean shrinks due to cooling and crystallization, and the cumulates at the bottom are very dense. This is the only plot I will show today, which is actually a quantitative result. So this is based on Bucharest's phase diagram, and we'll show his phase diagram later. His phase diagram doesn't have aluminium in it, but we also tried to consider the effect of aluminium on the densities of bridgemanite, for example. This is just a density profile that comes out from such a scenario. So the bottom 9% or 8.5% in the green scenario, where some disproportionation is also accounted for. Let's say roughly the bottom 9% of the mass of the BMO are extremely dense. They're more than 250 kilograms per cubic meter denser than the overlying mantle, and they would never be entrained by mantle convection. I mean, we still have to show this. My student Mohammed is working on this right now in models, but we're not expecting that these ever get entrained. So this is a problem, because we should really see this layer, right, at the bottom, and particularly this blue layer or green layer, and it should be depending again on the initial mass of the basal magma ocean, tens of kilometers at least thick. But this is something, and it should be global. It should be covering the whole core mantle boundary in this scenario. And this is something we don't observe. So the BMO was not isolated from the rest of the mantle somehow, or it didn't crystallize by fractional crystallization due to cooling, or both. I think both is pretty much the same thing, in fact. But just to drive this point home, this layer should be a global layer predicted by this simplified scenario of isolated BMO cooling and fractional crystallization. Doesn't produce piles. The LLSVPs are inferred to have an iron anomaly of about 2% or a few percent. I will also show another plot later, maybe tens of percent based on more recent work. But here this green layer, so maybe 10%, but this green layer has 40%, right? So that's not realistic. This scenario is not realistic. So there's, in particular, the densities, we have a good constraint for the densities, because just dynamically, the LLSVPs are piles and they are not a deep dense layer. So there's a mismatch between the geophysical observations, and that's really the problem I'm trying to address here. A mismatch between geophysical observations and the predictions from simple magma ocean crystallization, basal magma ocean crystallization models. Okay, so what can we do? So there has to be some BMO mantle interaction or coupling, or however you want to call this. So of course, there's the first thing you think is just the interface, BMO and the mantle. At the interface, depending on BMO initial composition. So in this case, the initial composition is over here, right? And this is in this equilibrium with the mantle, which is over here. The thermal divide is between the BMO and the mantle. So by the way, this is the Bucharest phase diagram that I was talking about, the ternary phase diagram. we have, this is just an MgO, FeO, SiO2 system, very simplified. But yeah, that's the one we have to take, because it's the only one really available. So if the BMO is in disequilibrium with the mantle, then you should expect some reaction at the boundary. And then you form these reactive cumulates, which are labeled here as diamonds. Oops, sorry. And the partial melts are these dark gray partial melts. The partial melts will sink back into the Basal Magma Ocean and mix with the Basal Magma Ocean. So the Basal Magma Ocean becomes more iron-rich in this case. The partial melts are actually here. So the mantle is red. The bulk, which is this pink box, I just call it bulk. It's probably a bad name for it. The bulk, this is the bulk boundary composition, is between, somewhere between the BMO initial composition, which is the white dot. Maybe I should write BMO here. Yeah, and if these, as you see in this animation, if these crystals get indeed entrained, then the Basal Magma Ocean mantle boundary gets inundated or whatever. Sorry, it's not the right word. Gets freed up again, and the reaction can continue. Otherwise, the reaction gets clogged up in this very simple scenario. And well, if you're interested, we can talk about how this gets entrained, and there we can derive some scalings for that. So anyway, if this happens, then you form a new layer again, and the Basal Magma Ocean should move into the direction of the composition of these partial melts, which were in dark gray, right? This is maybe inefficient if there's a thin layer that has to be continuously entrained. There might be also some two-phase region in the boundary, so this region might be much larger, so there might be more efficient interaction between the BMO and the mantle. But then a very recently, a very efficient way of mantle Basal Magma Ocean interaction has been proposed by Bolrao et al., also by Morison et al. And they propose a dynamical mechanism where actually flow crosses the boundary here and goes around in circles. So you have basically melting here, recrystallization here, and this is actually an efficient dynamical mode to pull out heat out of the Basal Magma Ocean and core. So it will occur at very low Rayleigh numbers, or well, the critical Rayleigh numbers for this process are very low. So it's a very efficient process, and well, it only occurs if you can have decompression melting. Decompression crystallization and compressional melting at the Basal Magma Ocean mantle boundary. But then it is a very efficient way to have interaction between the Basal Magma Ocean and the mantle. In both scenarios, you get kind of a similar chemical evolution, I think, in this ternary diagram. So the white dot, the Basal Magma Ocean composition, should move into the direction of the dark gray diamond. Here's another arrow. And then it should basically, as long as this is fast, so let's say for Bolrao's mechanism, this is fast, so there's no significant cooling happening when this is fast. So the BMO surfs along an isotherm, which is one of these black lines, towards the cotectic. I should say that this is really a simplified ternary. I should say that the cotectic is really much further over here, partly due to the effects of incorporation of aluminium and iron 3+ into bridgemanite. But this is supported by experimental constraints. This is a phase diagram at 120 GPa. So the Basal Magma Ocean will presumably surf further along this isotherm and get stuck somewhere here. And it's still kind of in equilibrium with the mantle, right? And then, as long as there is no significant cooling, it will stay there. And even then, if there's cooling, I'm not sure it can actually move down the cotectic, as long as it keeps on being in equilibrium with the mantle. So that's a question for the audience, really. Catch up with me, discuss with me. Tell me what you think about this. I'm not exactly sure what will happen at this stage if cooling occurs. I think it should just more or less remain at this point. If the BMO started already somewhere here, well, then you or say it started at the mantle composition, which is like the original Labrosse scenario. It would just move down here and then stay there, pretty much, I think. So you get the prediction is, well, you have pyrolite, you have the mantle, and then the Basal Magma Ocean cumulates consist of a two-layer sequence. First is MgSiO3 rich bridgemanite. I should have told this the whole time. This white dot was surfing through the bridgemanite stability field, because you crystallize a bridgemanite due to the reaction that is it's a reactive freezing. But you have to crystallize a bridgemanite to satisfy the mass balance. And then at the end, once you're over here, you will crystallize something that is more iron rich, moderately iron rich, I should say. But it also consists of a mix of ferropericlase and bridgemanite. Again, if you missed this, the bridgemanite stability field really extends all the way over here. Not in the Bucharest phase diagram, but in reality, in a realistic, what's going on? In a realistic system that incorporates aluminium, Fe3+, and so on. So this is in stark contrast to the crystallization sequence that I showed you before. We're not necessarily going into this very strongly enriched region down here with these blue colors and green colors and pink colors, the very high iron number. Okay, an alternative scenario is partial melting of subducted or somehow delaminated crust. Sorry, I'm seeing myself here. Yeah, well, that's okay. So in red here, this is supposed to be Hadean, Archean, depending on how long-lived the Basal Magma Ocean is. Basaltic crust that is, well, somehow recycled into the mantle by some geodynamic process. In yellow, this is the Basal Magma Ocean. And as the crust arrives at the Basal Magma Ocean boundary, it should melt, or at least partially melt. Why should it do so? Even the core mantle boundary temperature today is about 4,000 K, so higher than the Morb solidus. And the BMO mantle boundary in the Hadean should be hotter than that. The BMO is thermally coupled to the core, and the core should have been hotter than that in the past. There was no inner core, for example. So BMO mantle boundary was hotter than kind of mafic material. Solidus should have partial melting, and they should be efficiently mixed through the BMO and promote a reactive freezing there. let's look again at the phase diagram. Why should that promote reactive freezing? So if you start with the BMO now again at the composition, bulk composition of the metals or pyrolytic composition, and you add subducted crust. First of all, actually, you promote freezing because you're kind of moving up these other terms, right? But then as the temperature evolves, so here I consider also for cooling. So then instead of subducted crust, you will add partially molten crust when the mantle is cools over time. Oops, of course, this depends on how fast the mantle cools. Then the BMO will evolve down in the direction of partially molten subducted crust, which is somewhere down there. Now, of course, partially molten subducted crust or subducted crust brings a lot of aluminium and also iron 3+. And this is interesting. This is an important difference to the previous scenario. Aluminium drives iron disproportionation by the reaction that I write down there. So this reaction is, favored by higher aluminium contents, and you just keep on bringing aluminium when you bring crust to the BMO mantle boundary. So now instead of forming, so the first cumulus that you formed would be just, again, magnesium-rich bridgemanite, but then at some point you start to crystallize more iron-enriched and aluminum-rich bridgemanite. Yeah, because you can incorporate iron and aluminium into bridgemanite by this reaction that is shown at the top. Well, as the mantle further cools, you will move down into the other. So now you're on the other side, right? You're in the mafic cotectic, basically, if you want so. And as the mantle further cools to the core mantle boundary that we have today at 4,000. Well, is this Kelvin? Yeah, I think the 4,000 Kelvin. I think is maybe a lower bound for the core mantle boundary temperature today. We would be down there, and this would be the ULVZs. So if the ULVZs are remnants from the from the BMO, then this would be basically, sorry, oops. Well, I was supposed to write ULVZ. Well, it doesn't work right now. But the important difference of this second scenario compared to the first scenario that we talked about, where just pyrolytic mantle interacts with the BMO, here partially molten subducted crust or plain subducted crust interacts and reacts with the BMO. We start with the same kind of FeO poor MgSiO3 bridgemanite, but then we move into a moderately iron-enriched and also Fe3+ and aluminium-enriched bridgemanite. And I just keep this in this light blue color so you can remember it. I also write down, I'm not going to talk about this so much, if you use present-day subduction fluxes, which of course we don't know how the subduction fluxes were in the Archean, let alone Hadean. Just take these numbers and you assume some volume of the BMO, maybe 500 kilometers thick or something. Then you get to time scales, rough time scales of BMO freezing for 1 billion years. So this is faster than the 2 to 3 billion years that Labros suggested for just a fractional crystallization of the BMO due to cooling. So this should be more efficient. And this is kind of a lower bound estimate, right? Or upper bound in terms of the time scale, because the subduction fluxes might have been, well, much higher in the early Earth. Okay, so we have these two scenarios: interaction with a solid mantle, well, assisted by small-scale convection. I didn't talk about this, or assisted by the process that Bolrao et al. Suggested, in which case it would be very fast and efficient. But this has some assumptions behind it, this mechanism, I should say. In both cases, you first form this FeO core magnesium-rich MgSO3 bridgemanite. And this is a very good candidate to form these beams that I've been talking about. You can also check the more recent paper by Anna Guscher, I should say, and also the other two talks that I advertised and that I will advertise again in a few slides by my students. And then in the former scenario, you have this moderately iron-rich bridgemanite plus ferropericlase. So this is dense, but moderately dense. So maybe it could explain the LLSVP piles. And the other one is also moderately iron-rich, moderately dense, perhaps. We have to look at the quantitative results. If you're interested, talk to me. Maybe I already have more quantitative results by the time Golschmidt really rolls around. So let's compare these two scenarios. So sorry, here's this is supposed to be cyan instead of orange. I just changed the color scale right before I recorded this. So this is, but these are the same scenarios 1 and 2. Second scenario with iron disproportionation driven by aluminium delivery by subducted crust or delaminated crust. So how do we test this? This is paper by Kenny Vilella et al. And he uses geophysical constraints to infer the density anomaly. No, density anomaly would be one of the geophysical constraints, and VS, VP, and so on, to infer the composition of the LLSVPs. And so at the horizontal axis, this is bridgemanite percent here for these two panels, and here's aluminium weight percent and oxidation state pretty much. And on the vertical axis, this is iron content, calcium perovskite content. So there are a lot of trade-offs, and we cannot be for sure how the LSVPs look like. But one thing we can conclude in this plot over here is that there's a beautiful trade-off between calcium perovskite content and bridgemanite content. And if you ignore this, well, this little shading down here, which is highly improbable, then this implies that there is 0%, or maybe a very few percent in this shaded area, 0% ferropericlase in the LLSVPs. This is a major result from this paper. There's a fair amount of bridgemanite. There's also these yellow colors, which are the most likely parameter space. There's a fair amount of calcium perovskite as well, based on this kind of geophysical inversion of the LLSVP composition. But there's also a fair amount of aluminium here, Al2O3 weight percent around 10%, and iron 3 plus over sum over our total iron basically is very high. So the oxidation state is apparently quite high, which lends credibility to our second scenario, the scenario with the reaction with the subducted crust. But yeah, talk to me if you're interested in more details, or if you want to discuss further. Well, I would just want to quickly go through geochemical constraints. There's tungsten constraints. There's this nice paper recently by Andrea Mundel-Petermeyer, and you can't really see this in the red box. Very hard to see on this plot, but this is the tungsten constraints of a bunch of samples from different locations. There's the helium constraints. And Andrea argues that you need at least 3 N members to account for this data. Well, my question is, do we exactly know where these N members are? Maybe I should read the paper again. But in particular, do we know where in the mantle they are? I mean, first of all, where are they on this plot? Is it possible to shift 3 up, for example? Just for example, where are they in the mantle? For example, these beams or blobs, which may contain one primordial reservoir due to BMO crystallization, as I just mentioned. Could be another, it could be another reservoir and maybe host one of these end members. Or maybe they did not record, maybe the BMO did not record any anomalous tungsten ratios, even though I'm quite convinced that the BMO was already there before the moon forming giant impact, and we can discuss that if you're interested. The other type of geochemical constraints for the early Earth comes from the short-lived radionuclide or its daughter product, 142 neodymium. And this paper by Chung and Jacobson, they compiled the 142 neodymium data over time. And they argue that mantle mixing, they have very simplified models of mantle mixing, reduced the amplitude of these anomalies. Well, maybe this is just also related to the time scale. This is like a bit of a provocative thought, but maybe this is also related a bit to the time scale of BMO freezing. If BMO freezing took 1 billion years or 500 million years or something like that, and then later on, of course, you have mantle convection, but this could, BMO freezing would release in the first place some type of 142 anomalies. If we had data from the Archean, maybe this would be an idea that could be tested. I'd have to think about it, but depending on whether you have the positive and or the negative anomalies in the first and the second kind of reservoir. So I'm talking about the gray and the, instead of going back, here the gray and the orange, or the gray and the cyan in the previous color code. So these would be 2 reservoirs for the negative and the positive neodymium anomalies. And if we had more data from the Hadean, we could actually test that. I want to point out, as I mentioned several times, that you should check out the talks by Matteo Desiderio and Anna Gilche, because they will also discuss, well, first of all, they will discuss mantle convection models and these beams and what happens to them under which conditions, but they will also discuss, for example, what happened around 3 to 4 billion years ago. Another question I have for the audience is, how can we bring the previous slide with 182 tungsten and helium, and this slide with 142 neodymium, all in one picture? So, so basically, we want to measure these anomalies at the same sample, maybe more anomalies, and then paint a full picture what happened in the Hadean and in the Archean. Well, in the Hadean we don't have data, but that's eventually what we're after. Just a quick discussion about other terrestrial planets. Episodic resurfacing of massive amounts of crust should have occurred on Venus, is thought to have occurred there, and there's even some evidence for this, for actually subduction on Venus, even though there's no plate mosaic on Venus. There's isolated subduction zones. So this should have led to efficient BMO reactive crystallization due to the process we suggested here. So I disagree with O'Rourke that, so I don't think there is a BMO on present day Venus. Well, Mars has a stagnant lid, so maybe, but this is also a speculation, the Basal Magma Ocean on Mars is more, if it ever happened, if it ever or stabilized is more likely to survive. So I think you can read take-home messages, and I read them in the beginning. I will just say that I'm very happy to discuss quantitative recent results through Zoom, and if I have them in the next 2 weeks, chat and discuss more details. Yeah, email me or contact me through the Golschmidt apps, whatever will be there. And I'm also advertising a talk, which is a little bit of an overview talk. Thank you for your attention.